My name is Markel, and I'll be presenting our work to create a unified batch hierarchical reinforcement learning framework for pedagogical policy induction with deep Bisimulation metrics. Our framework is named MTL-BIM, and it unifies the pedagogical policies of two different intelligent tutoring systems into a single reinforcement learning policy. We achieve this by learning a unified latent space between the two policies using a variational autoencoder. Then we train a model-based deep RL policy in latent space to maximize the student learning on both intelligent tutoring systems. Our results show that students who use our pedagogical policy achieve significantly higher and more efficient learning in both intelligent tutoring systems. In summary, this is the first work to propose and empirically evaluate a unified deep RL framework for pedagogical policy induction across two ITSs. These are the two intelligent tutoring systems we use for our studies. On the left, we have DeepThought, a graph-based system to teach logic proofs. On the right, we have Pyrenees, a text-based system to teach probability concepts. In both intelligent tutoring systems, the pedagogical policy must decide whether to show a problem as problem-solving, or PS, or as a worked example, or WE. This is the architecture of our MTL-BIM framework. On the left, we show how the observation from each ITS is run through the encoder of a variational autoencoder to get the latent representation. Then we make the L1 distance between the two latent spaces be the same as the Bisimulation metrics between the two spaces, thus learning a shared latent space and making more similar states be closer to each other in latent space. Finally, we train a model-based RL algorithm in latent space to maximize the rewards. In this case, the rewards are the learning of the students in a historical dataset of student-tutor interactions. On the right figure, we can see all the neural networks that form our architecture. We performed two empirical studies with college students. In the DeepThought study, we compared the students who used our MTL-BIM framework against another three policies: an expert design policy, an RL-based DQM policy, and a problem-solving only policy. The figure on the left shows that both PS-only and MTL-BIM significantly outperform both the experts and DQM policies in terms of post-test scores. And the figure on the right shows that MTL-BIM outperforms PS-only in terms of learning efficiency. Next, on the Pyrenees study, we observed that students who used MTL-BIM outperformed the students in both the DQN and expert policies in terms of normalized learning gain, or NLG, and also in terms of isometric normalized learning gain, or ISO-NLG. In conclusion, our framework unifies the pedagogical policies of two ITSs into a single shared policy, and we show that students who use the MTL-BIM system learn more and more efficiently than students in the other policies, as shown by our empirical studies using DeepThought and Pyrenees. We believe our framework provides a step forward in unifying different learning systems and can be used to improve student learning. Thank you very much.